Hi, this is Professor Cummings. I'm coming back to you with the continuing this little series on solving derivatives or understanding what a derivative is. So, what is a derivative? Now, we went through what a function is, and we went through the definition of a derivative and why you would want to know what a derivative was. So, this next video is going to be on how do you actually solve for a derivative. And you see this slide here that we have. Let me go and put my laser on. You know, how do you solve a derivative? So problem solving, and here you recognize this is the definition of a derivative, one of the definitions of derivatives. Most of the derivative definitions we gave were just in verbally giving you a definition. This one was the one mathematical definition of a derivative, and I'm going to show you how to use this one today. Now, on a little side note, I want to spend a few minutes pointing this out because I don't want to confuse anybody. We have been looking at a couple of notations. They're only notations. They don't change the nature of the problem that we're looking at. When you have a dy over dx, that's what's known as the Leibniz notation. That's one of the most common ones you'll see when you want to look at differentials or derivatives. So dy dx or dy over dx is the first derivative. D squared y over dx squared is the second derivative. So then when you have a Lagrange notation, which is the one that we see quite a bit as well, is f prime and f double prime of x. And this is one of the most common types of derivative notations. And then there's one that you see a lot in kinematics and other forms, but it's not quite as common as Leibniz and Lagrange, is Newton's notation, which is just the dot notation. So be aware of that as we go through and carry on from this point forward. So we've gone through, like I said, what the definition of a derivative is. We've gone through the applications of a derivative, why you would want to use it. And we've even gone through and tried to understand where this definition comes from. Now, we looked at that in terms of this definition of a derivative, the slope of a line tangent of a line at a tangent point of a function. And this was the function that we'd been looking at in the last couple of videos, where f of x is equal to x squared. And we proved that one in the last video. If you have a description, a link in the description box if you want to see what the last video showed you on that one. But we went through and proved that or showed how this type of equation comes about as a definition of a derivative. In the way this comes out is this is essentially looking at the rise and the run, the rise over the run, so the slope of the tangent line as h approaches 0. And this is what tells us that we're looking at an instantaneous rate of change. So we're looking at the range as at an infinitesimally small point in time. Alright, so how can you use this to find the derivative? Well, let's go ahead and start with our original derivative, our original function, and take its derivative. So remember, this is our original function. So f of x is x squared, and I'm just saying f of x is equal to y is equal to x squared, all the same thing, and it's going to change how our notation looks. So if we plug this into our definition of derivative, what we end up with is saying that the derivative f prime of x, which is also equal to dy dx, is the limit as h approaches 0 of x plus h squared minus x squared. This being the f of x, this being the f of x, and the second coordinate is over h. So we got the first coordinate, the second coordinate. So this is a rise over the run, different change in rise, change over a run. So the slope of the line. And as we go through this equation, I'll go through it fairly quickly because I just want you to see this laid out. So if we FOIL this out, we end up with x squared plus h squared plus 2xh minus x squared over h. And we can simplify this a little, just drop in the parentheses. Now we can see we've got x squared plus h squared plus 2xh minus x squared over h. You can see that the x squares are going to cancel out. And we can factor out the h. So we end up with h times the quantity of h plus 2x over h. And these two h's will cancel out. Just clean it up a little bit more. So still the derivative, f prime of x is equal to h plus 2x. Again, using the limit function as h goes to 0. Now, if we take this h all the way to 0, we end up with a derivative of f prime of x is equal to 2x. And we could also say dy dx. So we went through all of this algebra, and we came to the conclusion that the derivative of x squared is equal to 2x. So this kind of shows us what the derivative is, and we can see, as we look at this function, what that actually means is that any function, any point input, value of x in this function, if you take a line tangent to it, this derivative will apply. So we can see the slope of any point, or the slope of any tangent point on this function will be able to match with this derivative, will correlate to that derivative. Now that comes to another very important point. If we take this function, just copy it over to another page, we've got f of x is equal to x squared, our original function, and here's the table that we were looking at originally when I was defining what a function was. X and x squared, f of x is x squared. And we look at this as the derivative, f prime of x is equal to 2x. This tells us something else. What this tells us is that f of x can also be represented graphically as well as in the table, because we're looking at every point on this line. The derivative of each point line has a tangent point, and since that tangent point can be described as this derivative of 2x, if we plot each point of x on this line, we'll end up with another graph, and this graph represents the derivative of x squared. You can also represent it as a table, as a second output. Again, for every input x, we end up with this output, which is the first derivative of that function. All right. So that tells us one important thing, the thing that I was trying to drive at, that the derivative itself is a function. It follows the definition of the function that we were speaking of. Now, for every function that we come up with, if we wanted to take a derivative, we don't want to go through that limit method of finding its derivative. That was a cumbersome method, even with a very simple function of f of x is equal to x squared. What we're going to want to do is use some of the rules of derivatives, which can help us go through these derivatives a lot faster, a lot more, with a lot less drama, if you will, when coming up with our solution or finding that derivative. So what I'm going to do in the next video is we're going to go through several methods of finding derivatives, just following the rules of derivatives that we know mathematically are rules of derivatives. This is Professor Cummings, and this is just another video helping you understand what a derivative is as well as how to use them. Thanks a lot.